I'd like to thank Professor Pe for inviting me to this nice conference, where it's very nice to give a talk enjoying this nice view. And maybe it is good for the audience. If you get bored with my talk, you can enjoy the view. So I gave us talk about a similar topic in the London conference of 2011, and that time I talked about mainly about the function field case, and so this time I would like to focus more on the number field case. And the London conference was titled the Arithmetic of Function Fields, and this conference is titled Arithmetic of Function Fields and Related Topics. So I think this is justified. So this is a joint work with Ozeki, joint work with Yoshiyasu Ozeki at RIMS. So let's fix some notations. So let K be a global field. And so GK, the absolute Galois group. So K bar is a separable closure. And consider decomposition group G sub B. So I fix an embedding of K bar into KB bar, decomposition group. So V is a finite place, any finite place of K. And let's consider Galois representations of GK. So for the moment, let me state rather vaguely. So this is just a continuous group homomorphism from this topological group to GL of something, and so V is a finite dimensional vector space over some local field. So E lambda is a local field. And so typically this is QL. Yeah, maybe we can assume this is QL.
So it's not required that it has the same characteristic as K?
No, I don't assume. But actually, in the function field case, both are characteristic P, and in the number field case, both are characteristic 0. In my case, and suppose we are given another representation, prime, and my basic question is if so I denote by V bar the V mod lambda. So this is actually choosing a lattice T, and it is T mod T lambda T, where T is a lattice in V. So it is a free module over the integer ring of E lambda, which is Galois stable. And in fact, this so this is a Galois representation over the residue field, and its isomorphism class may depend on the choice of T, but its semi-simplification does not. And so, but let me just put it as this. And my basic question is, so if V and V prime are congruent modulo lambda, then is the whole thing actually isomorphic? But in general, this is absurd. So today I consider local thing as GV representations. Then V and V prime isomorphic as GV representations. And in fact, we can only deal with its semi-simplifications. So I write here SS. So so this means their semi-simplifications are congruent. Then is the semi-simplifications of V and V prime are isomorphic. And in general, this is impossible because so we have the well-known deformation theory, Galois deformation theory. And so this theory controls the liftings of V to V bar to V. So in general, there are so many liftings. So the natural question is to impose some other conditions then the original representations that the isomorphic. So another way to formulate this question is, are there any natural conditions to make the lifting unique? And as I said, I treated the function field case in London. Function field case. So here K and E are function fields. Fields. And V and V prime are coming from T motives. But I don't state precisely today. And so today, so this Busan. So this is not the name of a mathematician. So today, K and E are finite extension of Q. And we fixed so V a finite place of K, and so we fix some integers n, b, e, so we fix these data. Then there exists a constant depending on the degree of Q, and N, B, E, and QV. So this QV is the residue degree. Residue degree. Anyways. The order of the residue field, and such that in fact this can be given explicitly, max of B plus 1 and 2 times Q. Maybe this explicit form is not very important, but such that for any prime number greater than C, and all any finite place of K lying above L, and any finite place of E lying above L, and any Galois representation of a certain type. And I will explain this notation later. So anyway, suppose we are given two representation Then if v and v prime are congruent, mod lambda as GV representation and GU representation, then V and V prime are isomorphic as GV representation. So I impose this further condition here. So in particular, if these are congruent modulo as GK, I mean global representation, then this implies both too. So in applications, we can usually assume this condition. And about the notations, so I explained this briefly, so I think this is okay. So just put same simplification on the both sides. And this set, so this is a little bit complicated, but G E lambda N K U B E V. So this is a set of Galois representations, n-dimensional representations over E lambda and of a certain type. And I will explain more precisely later. But this means kind of geometric so I assume several properties which are supposed to which étale cohomologies are supposed to have, and yeah, and we fix several, impose several conditions. Before stating precisely, I'd like to explain some motivations. So motivation. So it is a conjecture by Rasmussen and Tamagawa, and so they considered such a conjecture. So K is a number field, finite extension, and G is an integer, positive integer, and they considered so L is a prime number, and let's consider the set of Abelian varieties. Abelian varieties over K of dimension G, which have good reduction outside L, and which have whose Galois representation on the L torsion points is of the form sorry. So this AI are some integers. So in general, the Galois representation on this L torsion point are close to GSP to G. So this is a very special type. So this chi is a cyclotomic character. Mod L cyclotomic character. So this is a special kind of reduction, L torsion point. And their conjecture, Rasmussen and Tamagawa, is that this set is empty if L is big enough. So by a famous theorem of Falting's, this set is always finite, and but their conjecture is that if you take the union for all L, then the set is still finite. This means that this is empty for all. Sorry. In fact, you should take isomorphism classes, but anyway. So yeah, and behind this conjecture, so their motivation is another conjecture by Ihara, and I don't explain it today, but anyway, so they consider this conjecture, and some known results are, for example, if K is Q or a quadratic field, and there is an elliptic curve, then this is true. So this is by the original paper, and their recent paper, preprint, they completed some unknown cases, and so if this is Galois and the exponent is less than or equal to 3 and g equal 1, so this is by Rasmussen Tamagawa, and what else? Maybe K is Q case, and G is at most 3, I guess. I don't know. Yeah, maybe most 3. Then this is by the same paper, and yeah, they also proved that this in general, assuming the general Riemann hypothesis. And yeah, and also if we restrict here everywhere semi-stable abelian varieties, then we can prove this in general. So A is good reduction outside L. So if we assume it has semi-stable at all places over L, then we can prove this in general. And so this is due to Ozeki. And Rasmussen Tamaga also. And yeah. Also, if the Galois image image of the Galois representation is abelian, yeah, if you limit those A for which the associated L-adic representation is abelian, then this is true by Ozeki. So this is another paper which is a preprint yet. And some QM multiplication abelian surface case was treated by Arai. Maybe so I think this is still a preprint. Anyway, there are such results. And so our theorem is a kind of systematization of Ozeki's method. And corollary of our theorem is the following. So we generalize somewhat. So K, G, E, V, L, semi-stable. Abelian varieties over K of dimension G. Such that good reduction. Potentially good reduction. At V. So we only need just one place where A has potentially good reduction, and yeah, this torsion point. So this is always assumed. And we also assume that this A has semi-stable reduction. Yeah. Sorry, I have to continue here. Reduction over some extension. So this Ku is such that the absolute ramification index divides the given number E. So the condition looks rather mild in that we only assume good reduction at V, one place. But in fact, this condition, semi-stable, is rather strong, and it is very difficult to remove this. And in any known case where the semi-stable condition is removed, they use a rather analytic method, and like the Riemann hypothesis or some analytic number theory, and so we can do only this. Yeah. Maybe. In fact, this is not a direct corollary of the theorem, but a corollary of a certain version of the main theorem. And if we directly use the theorem, we have to remove this. But anyway, and maybe for illustration, let me give another corollary. So this is even another version of the theorem to is that fix a finite set of primes and fix prime in S and fix integer k. Then there exists a constant such that so this is about representations coming from modular forms. Then for any level n, and this is assumed to be square free, square free outside S. So it can contain many primes in S. And but it should not be divisible by Q. And for any modular form, so this is a normalized eigenform. Then there exists no prime L greater than C such that AP congruent to so there are no big Eisenstein-like prime. So this is well known for each modular form F. So this is well known for any fixed n and fixed k, but I think it is not so obvious that if you move n, then there is such a bound C. Okay, so this is these are typical corollaries, and next I like to explain the conditions on the Galois representations.
Is there a relation between K1 and K2?
No, just maybe just K1 plus K2 K something like this. Yeah, only this, I think. So the set rep what UB is okay, the set of is set of row and first condition is semi-stable. At V, this means that the action of the inertia is unipotent. Yeah, so so this V, it does not divide L. So in this case, semi-stable means that the inertia action is unipotent. And second is this is E integral at V and of Weil type. So since the inertia action is like this, Frobenius at V acts on the semi-simplification of S of V as a representation of GV, And so we can consider the characteristic polynomial. And this is a priori in has coefficients in E lambda, but it has so this E integrality means that the coefficients are in the global integer ring of E. And yeah, so this kind of thing is usually satisfied with Q if you consider the L-adic cohomology or L-adic Tate module, etc. But if we want to consider some cases with coefficients like CM Abelian varieties or Hilbert some GL2 type Abelian varieties, then this kind of larger E is very useful. And so the third condition is that V becomes semi-stable over K prime. So this U is prime over L. So this meaning is a little bit different, and with so this semistability is in the sense of Fontaine. So this is defined by saying that this kind of thing, this is maximal dimension. Anyway, so and yeah, then semistability means that this representation is Hodge-Tate. So as V has Hodge-Tate weights are in a bounded period interval, and V is of type G, and so this condition says that the sum of value weights of V equals 2 times sum of Hodge-Tate weights of V. Here, so this notation means the sum of elements in it, and WV of V is the so I allow multiplicity. So this is the multiset of value weights weights of V at V. So I said that Frobenius acts here, and their eigenvalues are algebraic integers, and they are I didn't explain this Wei type, but so this means the roots are all Wei integers. So this means all complex conjugates has the same absolute value. So the absolute value the absolute values of eigenvalues are qv to some integer over 2, half integer. So this is the set of V's, W's with multiplicity, and H T of V U. So this is the multi-set of Hodge-Tate weights. So this is the integers which appear here. So these are Tate twist, and these are the set of these integers hi, and this condition is satisfied by the étale cohomology of proper smooth, projective smooth varieties. Anyway, so these are the conditions I need, and I think these definitions explain somehow the proof. Now, so finally, I just combine these conditions to give to prove the theorem. So let's start with the semi-stable condition. If the representation is semi-stable, so I assume that it becomes semi-stable after finite extension, but this is technical, and let's assume it is E is just 1, so it is already semi-stable. Then by a result of Caruso, there is a bound of the so-called tame inertia weight. So this is a result of Caruso, and so if the representation is like this, then this tame inertia weight is basically these integers. And it says that if L is large enough, these integers cannot be arbitrary. There is a bound. And this was originally a conjecture of Serre. So this is in his famous paper of 72 about the open image theorem. It's section 113 or something like that. And it was completely proved by Caruso a few years ago. And anyway, so there is a bound on this exponent. And next, again by another theorem by Caruso and Savit, this is enough to bound the Hodge state weight. So this is Caruso Savit. So this says that these tame inertial weights and Hodge state weights are coincide in certain good cases. So then our condition G, the equality, can be used to bound the Wei weights using that equality. Then we get the bound of the coefficients of V. So this is at V. So this equality connects the two different places, V and U. So this is the nice thing. And yeah, and the same, we get the same for V prime SS. Then if and this characteristic is very sufficiently big, implies they are actually the same. And since the representation is unramified on this VSS, the characteristic polynomial of the Frobenius determines the representation. So this implies this. So this is the proof. Okay, thank you very much.